the conduction system of the heart. What I'm going to show you first of all is what happens in each cell when the electrical impulse is sent out from the SA node. This happens in every cell beginning right beside the SA node along the entire conduction system through the heart from the top of the heart to the bottom of the heart. When the conduction system sends out that impulse, it starts a waveform that starts up here at the top of the heart, and it moves across the heart in a waveform just like a wave coming in from the ocean to the beach. Okay? And then it collapses at the beach and it starts all over again. That's the way the waveform moves from the top of the heart down through the bottom of the heart. It gets down here, that wave is done, the heart muscle rests, recuperates, and gets ready to do it all over again. I'm experimenting a little bit here, so y'all bear with me. Okay. Now, in each cell of the heart, I talked earlier this morning about the sodium-potassium pump, right? Okay. So we're going to talk a little bit more about that sodium-potassium pump and what occurs in each cell when the impulse sends out from the SA node. So all right, inside each cardiac cell, you have potassium, and that's an electrolyte. So you have potassium inside the cell. And if you remember from biology, all cells are bathed in cellular fluid, right? Everything's not just dry. That's why there's so much moisture in our body, because each cell is bathed in a cellular fluid. All right, so inside the cell there is potassium ions, and they are positively charged. Okay? Outside you have sodium in the extracellular fluid, and you also have a little calcium. And these are calcium and sodium ions. And outside the cell, there is a net negative charge. Okay? If you remember anything about electricity, when you have electricity, electricity moves from pole to pole, from your positive pole to the negative pole. Okay? When the charge, let's say your positive charge, is not any stronger than the negative charge, then your object or whatever it is said to be polar. That means that it's not, the negative charge is not stronger and the positive charge is not stronger. They both are equal, so one is not pulling harder than the other. Think about magnets. If one is stronger than the other, it'll pull the weaker one toward it. So when your charge is equal, you're said to have, or the cells are said to be polar. To begin with, that's how your cells start out. You have the positive charge inside and the negative charge outside, but they are equal. So one is not pulling on the other. But when the SA node sends out an impulse, it changes the polarity. Okay? So what happens then is when the impulse strikes these cells, these cellular membranes become permeable. What does permeable mean? They allow things to pass through. If a membrane is permeable, that means that it allows something to pass through. So when the impulse first strikes the cell, it causes the membrane to become permeable. And what happens is you have potassium begins to move out of the cell. Not all of it, but some of it begins to move out of the cell. Okay? So now the charge is not equal across the cellular membrane, it's changing. So the first thing that happens is that potassium moves out of the cell. And the charge begins to change. Because before it was equal, now you have this positive charge moving out of the cell. So potassium moves out, and then sodium starts to move in, and a little calcium along with it. Mostly sodium, but a little calcium as well. So now the charge across here has changed. You've got positively charged ions moving out of the cell. You've got negatively charged ions moving in the cell, and they're not moving in equal amounts. So the charge across this cellular membrane now has changed.
So sodium is negatively charged?
Yes. Sodium and calcium, remember, are negatively charged. Okay?
So, but you've got positive beside each one.
Well, that just indicates that they're an ion. They're an electrolyte.
Okay.
Electrolytes are ions, which means they have lost or gained an electron. But the charge themselves, inside here there is a positive charge, and outside there's a negative charge. And because neither is stronger than the other, it remains neutral across that cellular membrane. But when that electrical impulse hits that cell, then it causes these changes to occur. You have the cellular membrane becoming permeable, potassium starts to move out, and then sodium and calcium begin to move into the cell. And when that happens, that's called the sodium-potassium pump. Now, when that impulse hits the cell and these things occur, it causes the cell to contract.
Say that one more time.
When these things occur, when the impulse hits this cell and it causes these changes to occur, the cell membrane becomes permeable, potassium comes out, sodium and calcium go into the cell. The cell charge has now changed. It's no longer polar. It has depolarized. Okay? It's no longer polar. And when it depolarizes, that cell contracts. Okay? And this moves in a wave-like form from one cell to the next cell. From the top of the heart all the way to the apex, or the bottom of the heart. And so as each cell contracts, it makes the whole heart muscle, well, let me back up. It makes the heart muscle contract from the top to the bottom, because it happens as it goes from one cell to the next. Okay? So, here you're polar, because the charge is equal across the cell membrane. When the electrical impulse hits a polar cell, it causes it to change. These things happen, and the cell contracts. So depolarized means they have contracted. And so as the impulse moves across the atria, it causes each one of those cells to contract, and so the entire top chambers contract and squeeze the blood from the atria into the ventricles. Okay? So then once the ventricles have emptied and the impulse slows down or is delayed in the AV node just for a moment to allow for the atria to completely empty into the ventricles, then the impulse starts to move down through the septum between the ventricles and all the way on down, and the impulse moves across the ventricles, and so it continues to cause those cells to contract, going all the way down to the bottom of the heart, or the apex of the heart. Okay? So we've gone from polar to depolarized, and once everything has depolarized, then it has to recover. It has to rest and get ready for the next impulse. Okay? So it's polar here, it's depolarized here. Once the cell has contracted, then it relaxes and potassium starts to go back in to create that positive charge inside, and the sodium and calcium start going back out of the cell. So potassium goes back in, sodium, calcium go back out. And so we were polar, we were depolarized, and now the cell has rested and gone back to its original state. And so now here we are repolarized. Okay? So polar, even charge across the cell membrane, depolarized, cell membrane is permeable, potassium moves out, calcium and sodium move into the cell, and the cell contracts. It depolarizes. Then, after it's contracted, it relaxes. Potassium goes back into the cell. Sodium and calcium come back out of the cell. And now it has repolarized. It's ready to start all over again. So that is what polarization, depolarization, and repolarization are. Depolarization is when the cells change and contract, pumping the blood from the atria into the ventricles, and then as the impulse moves on down across the ventricles, out of the ventricles, to the lungs and to the body.
Okay, so when you say it's in a wave-like form, it goes from the top down all the way to the bottom, that's where you get atrial depolarization and, okay. Now I get
Yeah.
it. Okay.
Yeah. Okay, so polar, depolar, this is going back to recovery phase. This is repolarization. Repolarization and recovery. So now once it's repolarized, it's polar and you're ready to go again. And it starts all over again, top to bottom. Okay? So now we got to put these things together. All right? When, let's say the SA node is about to send out an impulse. Everything is just, there's no activity, no electrical activity. So the SA node sends out an impulse to this cell and causes this chain reaction to occur. Polar, depolarization, repolarization in all the cells from the top to the bottom of the heart. Okay, so as the atria depolarize and contract, that is what the P wave represents on your cardiac complex. Remember that purple waveform that was at the beginning of that complex just now? When the atria depolarize, that first upward deflection from the baseline is the P wave, and that represents atrial depolarization.
So atrial
Depolarization.
represents the P wave?
The P wave represents atrial depolarization, because the P wave is what you get on your printout. The P wave represents atrial depolarization. Okay? Then right after the P wave, you had a little short space on the baseline, and anytime you have space just on the baseline with no upward or downward deflection, that means that no electrical activity is occurring at that time. Remember when the impulse stops or is delayed in the AV node? That's what that little segment right there represents. And there is this picture is on page 496 in your book. So you've got the P wave, then you've got, I got it kind of long, the PR segment.
So the PR segment represents the end of
Atrial depolarization.
Depolarization. And the beginning of.
Well,
Okay.
don't get ahead.
All right.
All right, so we've got the P wave that represents atrial depolarization. Then the PR segment represents the time that the impulse is delayed in the AV node.
So it's the PR segment represents the end of the P wave.
The end of atrial depolarization. Okay, then you have another waveform that goes down and then goes up, comes back to the baseline and goes down. And I'm just going to go ahead and draw the whole thing right now. Oops, it's kind of big. Okay. All right, so no electrical activity here. Then your next waveform, there's Q, R, and S. This begins ventricular depolarization. So at the end of the PR segment, that's when the impulse leaves the AV node and starts to move down through the bundle of His and the bundle branches, and you have this small little wave that's usually a negative deflection or downward deflection from the baseline, and that's the Q wave. Then it goes way up here, and this is the R wave. That is the, I guess you could say, the pinnacle of the ventricular depolarization. Because remember, the ventricles have more musculature than the atria do, and it is a much bigger event than atrial depolarization. Okay, so now we've got the Q wave, the R wave, and the S wave. So Q wave down, R wave up, excuse me, S wave back down to the baseline and a little below, and then back up to the baseline. Then you have this little section, I forgot what color it was just now. This is the ST segment. Once again, you have no electrical activity, it's on the baseline. And that's when the ventricles have depolarized. They're beginning to rest and recover. And this is the T wave. That's repolarization of the ventricles. I've got y'all completely boggled now, clear as mud. Okay, that's why I wanted to go over it today, so that you can have some time to get it to start to get the light to come on, so to speak. Okay, so if you look at the picture on page 496, that is exactly what I just drew right here. So for every heartbeat, this happens in your heart. Every heartbeat, this is the entire complex that prints out on the electrocardiogram. So it represents atrial depolarization, ventricular depolarization, ventricular repolarization. You got a question? I was hoping you did.
I'm just trying to.
There's one thing that's missing.
The intervals, right?
No, I'm not going to go over them right at the moment. We've got atrial depolarization, ventricular depolarization, ventricular repolarization. What am I not saying?
Say that again.
Atrial, right. You've got atrial depolarization, little delay. Then you've got ventricular depolarization and ventricular repolarization. What's missing? Shanika said it. Atrial repolarization. Did you see anything there that says atrial repolarization? No. What? I'm not getting there right now. Atrial repolarization happens at the same time that ventricular depolarization is occurring. It's just that the QRS complex, or ventricular depolarization, is such a strong and powerful event, and so it does not show up on the waveform because like she said, it kind of happens behind where the ventricles are depolarizing. That's such a big, strong event that you do not see atrial repolarization on the waveform. You just have to understand that it is occurring at the same time of the QRS complex. Okay? And then your T wave is ventricular repolarization. After the T wave, you have a little spot on the baseline where nothing is happening. Everything's getting ready to start all over again. And then the next thing that you'll see is another P wave that represents the beginning of the next complex and next heartbeat. Now, once again, let me just say this one more time. All of this happens in a second or less. And it does it quite efficiently for a long time. Questions?